Welcome everyone, and welcome to the AluVET Vocational Training and Education for the Aluminium Sector. This training is co-funded by the Erasmus Programme of the European Union. I am Jan Lukaszewski, the Technical Manager of the Aluminium Federation in the United Kingdom. The Introduction to Metal series of modules explains the simple theory of metals and of metallurgy, sufficient to enable students in subsequent modules to understand aluminium, its alloys, heat treatment, and how it is rolled, extruded, and/or welded. In this module, following on from the first module on elements, atoms, and metals, we shall learn how metal atoms form into crystals and how crystals behave. This project is funded with the support of the European Union. This publication reflects only the views of myself and the Aluminium Federation, and the Commission cannot be held responsible for the use which may be made of the information contained therein. Metal atoms firstly organize themselves into cubes. Then the cubes repetitively form into ordered crystals. We shall explore both the nature and formation of the cubes and how the cubes replicate into crystals. Then we shall examine the nature of crystals and particularly see that they consist of planes or distinct layers of atoms, all bonded together by the metallic bond. In this module, we shall learn what metallic crystals are, how they are constructed. We shall learn that crystals are the physical form of metals that we touch and handle. We shall learn why crystals enable metals to be deformed and reshaped, plastically worked. Why metal crystals can be worked or reshaped without failure. So let's start looking at metal crystals. When individual metal atoms bond together, they form into ordered arrangements by sharing the cloud of electrons. This unit cell is the smallest group of atoms. These arrangements are the unit cells that will form into the repeating pattern of crystalline structures. In the picture, we have a body-centered cube, a basic unit cell. Now, atoms form into these unit cells to minimize the atomic packing. So that's the closeness of how the atoms to get together, the strongest bond that the electrons can form. The unit cell allows the atoms to create the strongest metallic bond and the best sharing arrangement of the cloud of fast moving electrons. Different metals adopt different unit cells. Iron atoms organize themselves into a body-centered cube. A body-centered cube is where there is an atom in the middle of the cube. Aluminium, the atom that we are interested in, forms into a face-centered cube. In the middle of each face of the cube, there is an atom, face-centered cube. Magnesium forms into a hexagonal closed packed arrangement. So different metals adopt different cubes. The cubes allow the atoms to come together in the closest packing, which allows the electrons to form the strongest metallic bond. Now, aluminium atoms arrange themselves into a face-centered cubic unit. In the face of the aluminium cube, in the center of each face of each cube, there is an aluminium atom, and at each corner there is an aluminium atom. So there is an aluminium atom in the middle of each of the 6 faces of the cube, top, bottom, and 4 sides, and at the corner of each of the sides. Remember, cubes are 3-dimensional, so each face-centered cube has 14 atoms. I hope my maths is right. 1 in each corner, 1 in the middle of each face. Now remember, the reason a cube is formed, it allows the closest packing of the atoms, and the closest packing of the atoms allows the sharing of the electron cloud. So the electron, the fast-moving electron cloud, is 3-dimensional, and it is shared between all 14 atoms of the cube, maintaining the metallic bond in all directions and across all atoms. So far, we've spoken about one, but the aluminium face-centered cube is replicated by adjacent atoms, forming many, many identical cubes. Now, remember that cubes are 3-dimensional, so have 6 faces. Now, this means that adjacent cubes share one of the 6 faces. So we start off with a cube, and bonded onto the side of each of the 6 faces is another cube. And when the 2 cubes bond together, they share that wall of atoms. So the 4 corner atoms and the atom in the middle are shared. This means that adjacent cubes share one of the 6 faces and the 5 atoms, and this sharing goes on in 3 dimensions. Now, this repetitive translation of sharing of of aluminium atoms of the 6 faces of the unit cells with the adjacent unit cells in all 3 dimensions creates the crystals. So you have one cube, and that is shared by the adjacent cube, and that is shared by the adjacent cube, and that is shared by the adjacent cube. And that sharing is sideways and up and down. So by sharing the individual cubic, we are creating 3-dimensional crystals. So 3-dimensional crystals are formed by billions of adjoined face-centered cubes sharing the atoms. And it is the crystals that we touch and shape and form. So adjacent face-centered cubes form crystals. Now, if we look at the way the crystals are formed, we realize that in 3-dimensionals, if we look at the 3-dimensional crystals of adjacent cubes, and we move them about, we suddenly realize that the atoms have aligned themselves into layers. You can see this in the picture. If you look in the picture, you can see the cube and you can see how the cubes are replicated. But if you look very, very carefully, the atoms of a face are forming a plane with their adjacent neighbors. So these atoms organize themselves in a single dimension into layers. And technically, we call these layers planes. So if we spin the crystal around as I've done in the picture, you can readily see and appreciate the layered arrangement of atoms. So cubes form crystals, and when you reorientate the adjacent crystals, the adjacent cubes actually consist of layers or planes of atoms in a line, in a row. If we strip away the 3 dimensions and we simplify the crystals into 2 dimensions, what we see is that the planes of atoms are stacks of layers of atoms. So in very, very simplistic terms, crystals are layers of atoms. Now remember, the individual atoms have shared their electrons. So the individual atom protons are positively charged. They're not bonded to each other, but are held together in the crystals in all directions by the metallic bond of the electron cloud. Now, as individual atoms are not bonded together to specific atoms, but held together by the charge of the electron cloud, we can actually physically slide or move the atoms or planes of atoms over each other. We've got planes of atoms, planes of ping pong balls. Because they're not individually bonded together, but held together by the cloud of electrons, the metallic bond, we can actually move the planes of atoms. We term this movement sliding movement slip, because we slip the planes of the atoms over each other. Simply, we can force the layers of metals to slip easily past or over each other, and that is how we reshape metals. We term this ability to reshape metals ductility and the property malleable. The fact that the atoms are still held together while we reshape the metals by the metallic cloud is the reason why metals are ductile and malleable and do not fail or break. The metallic cloud holds the atoms together, so when we slip the planes of atoms, the atoms don't come apart, they don't fail, they're still held together by the metallic cloud. As the metallic bond that holds the clouds together is a fast-moving cloud of electrons, it doesn't break nor fail, but just reshapes and continues the atoms to be shared by the slipped atoms. Thus, the metallic bond still holds the atoms together. There is no loss in strength. The slipping of the planes of atoms past each other is what enables us to shape, reform, draw, extrude metals. I hope you've enjoyed this very, very short course. I hope you understand how atoms come together to form cubes, that cubes are shared together to form crystals, that if we look at the cubes in 2 dimensions, they're planes of atoms, and that by moving the planes of atoms past each other, reshaping them, slipping them, we can reshape, extrude, hot roll, cold roll metals, and that the planes of atoms don't come apart because they're held together by the metallic bond. I hope you've enjoyed this module, and please see some further reading. Thank you very much.